In a traditional wireless connectivity, communication is built on a simple single-lane model. A device connects to an access point through one specific link on a single frequency. While this works well for basic tasks, it limits how much data can move at once and creates a single point of failure if that specific frequency becomes crowded or suffers from interference. To break past these limits, we move toward a multi-link architecture. Instead of treating every connection as an isolated tunnel, we introduce multi-link devices. In this setup, a single device doesn't just exist on one frequency. It operates across multiple links simultaneously. You can think of an access point in this architecture as a collection of multiple integrated access points working in unison, while a mobile device acts as a collection of multiple stations working together. The magic of this system lies in how it manages these multiple connections without creating chaos. To keep everything organized, the device uses a unified identity called an MLD MAC address. This single high-level address acts as a master controller, allowing the network to manage the device as one cohesive logical entity rather than confusing swarm of separate connections. This unified management is what allows the device to coordinate communication across different links seamlessly, switching or combining them to maximize throughput and reliability. However, we don't lose the ability to be precise. Even though the device has this master identity for high-level coordination, the individual stations within that device maintain their own unique MAC addresses. This means the network can still perform granular addressing, reaching specific subcomponents or sublinks when necessary. By combining a single master identity for management with individual identities for specific tasks, the architecture achieves a perfect balance of high-level coordination and low-level precision. When a device wants to take advantage of multi-link connectivity, its first challenge is finding out which links are actually available. It can't connect to multiple paths at once if it doesn't know they exist. To solve this, access points broadcast specific multi-link information within their standard beacon frames and probe responses. This allows a client to see at a glance that an access point is operating across more than one frequency or channel. However, knowing a link exists is only the first step. To establish a truly cohesive connection across a multi-link device, the client needs a holistic view of the entire set of links. This is where neighbor reporting becomes essential. An access point will share a reduced neighbor report that describes its other affiliated links. This report provides much more than just a list of channels. It includes critical timing information known as the target beacon transmission time for every other link in the set. By sharing these precise timestamps, the access point tells the client exactly when to wake up and listen for beacons on the other links. This synchronization is vital because it prevents the client from having to scan every single channel blindly, saving significant power and reducing latency. As the client learns about these affiliated links, it also needs to understand what they are actually capable of doing. To manage this, the system uses profiling to advertise the specific capabilities of each link. Depending on how much information is needed, the access point can send out a complete profile, which provides a full picture of all features, or a partial profile. Using partial profiles is a clever way to keep management frames small and efficient, ensuring that the device gets the necessary details without overwhelming the airwaves with unnecessary data. Through this combination of discovery, timing synchronization, and capability profiling, a device can seamlessly transition into multi-link state. When a device wants to connect to a network using multiple links, the process begins during the association exchange. This is the moment where the device and the access point formalize their relationship and agree on how they will communicate across different frequencies. For this multi-link setup to be valid, both the request and the response frames must include a specific set of multi-link elements that communicate the capabilities and intentions of each side. During this exchange, the access point has a significant amount of flexibility in how it handles the request. It doesn't have to accept every link the device asks for. The access point might decide to accept all the requested links. It might choose to accept only a subset of them, or it might reject the multi-link request entirely. However, there is one critical rule to remember. If the access point rejects the specific link that was used to receive the initial request, the entire multi-link setup fails immediately. Once a connection is successfully established, the network treats the multi-link entity as a single logical unit. To keep things organized, the access point assigns a single association identifier to the entire multi-link device. This means that even though the device is communicating over several different links, it shares one unified identity within the network. Finally, there's a requirement regarding how these links are physically organized. To ensure that the communication is efficient and free from interference, all the accepted links must operate on different non-overlapping channels. This separation allows the device to truly leverage the benefits of multiple links, moving traffic across distinct paths without the signals stepping on each other. In a multi-link environment, a device isn't just communicating over a single frequency. It is managing multiple simultaneous connections across different links. For this to work seamlessly, those links cannot operate in isolation. They must be temporally aligned. If the timing across these links begin to drift apart, the entire coordination breaks down. You might find that a frame sent on one link arrives at a moment when the receiver is expecting a completely different timing pattern, or worse, a device might miss a scheduled wake-up window entirely because its internal sense of time is slightly off. To prevent this, we have to manage the relationship between different clocks driving these links. Even high-quality hardware experiences clock drift, where internal oscillators fluctuate slightly over time. To maintain perfect coordination, the system must actively correct this drift. We enforce a strict constraint on the difference between any two timing instances within a multi-link device. Specifically, the time difference between any two links must stay within a window of 30 microseconds. Maintaining this tight precision is what makes coordinated multi-link actions possible. When we need to perform a simultaneous transmission across multiple links, or when we need to synchronize the exact moment a device wakes up to listen for data, that 30 microsecond threshold ensures everyone is acting on the same schedule. By constantly monitoring and correcting the drift between these links, the system ensures that the multiple physical connections behave as a single cohesive unit rather than a collection of independent drifting signals. This temporal alignment is the foundation that allows for high-speed, low-latency coordination we expect from modern multi-link operations. Once your device has established multiple active links, the next challenge is deciding how to actually distribute your data across them. Without a specific plan, the system follows a simple default behavior where every single traffic identifier is mapped to every available link. This means that whether data is moving up from the device or down from the network, it can travel over any connection at any time. While this is easy to implement, it doesn't allow for much optimization. To get more control, the system uses a process called TID to link mapping. This allows the device and the network to negotiate a more intelligent distribution strategy. Through a series of requests and responses, the device can move away from that all-to-all approach and instead group links into specific subsets called link sets. By assigning certain traffic identifiers to specific link sets, you can perform precise traffic regulation. Think about how different types of data have different needs. You might want to take latency-sensitive voice or video traffic and pin it to a highly reliable, stable link to ensure there's no drops. At the same time, you can take bulky, non-urgent data transfers and send them over a high-throughput link that is optimized for raw speed. This mapping also gives you granular control over the state of your connections. You can define links as enabled for specific types of traffic, ensuring they're ready to work when needed, or you can mark them as disabled for certain identifiers. This is incredibly useful for managing power consumption or reducing interference, as it allows the device to keep certain links quiet unless a specific type of data requires them. Instead of treating all links as a single pool, you're turning your connections into a coordinated system tailored to your specific data needs. When an access point has data waiting in its buffer for a client, it needs an efficient way to let that client know there's information ready to be retrieved. In a traditional single link setup, the access point uses a traffic indication map to signal this. This map contains a bitmap where each bit corresponds to a specific client's association ID. If a client sees its bit is set, it knows it needs to wake up and ask for its data. However, when we move into the world of multi-link technology, things get a little bit more complex. A client might be connected to an access point across several different links simultaneously. If the access point simply says, "I have data for you," without specifying which link it is sitting on, the client might waste energy and airtime checking the wrong connection. This is where multi-link traffic indication map comes in. Instead of just providing a general notification, the access point can use a more granular signaling method. This approach includes specific bitmaps for each individual link. Each of these bitmaps maps directly to the client's association ID, but they are categorized by the specific radio link they belong to. When a client examines these per link bitmaps, it receives a very clear instruction. If the bits for a specific link are set, the client knows exactly which link is holding its buffered frames. This allows the client to target its retrieval efforts using a trigger frame or a poll on the precise link where the data is actually waiting. If the signaling is absent, or if no bits are set for a particular link, the client understands that there's no immediate data waiting on that specific path, and it can choose to use any other enabled link to check for updates. This coordinated approach prevents unnecessary radio activity and ensures that data is retrieved as quickly and efficiently as possible across the entire multi-link connection. When a device operates across multiple frequency links at once, a fundamental capability determines how it handles data, whether it can support simultaneous transmit and receive, often called STR. In an STR configuration, a device is built with enough isolation to transmit data on one link while simultaneously receiving data on another. The internal signals from the transmitter don't leak enough to drown out the incoming signal on the second link, allowing both links to operate fully and independently at the same time. However, many mobile devices are designed as non-simultaneous transmit and receive, or NSDR, because these devices are often compact to save space and power. They lack the heavy shielding or physical separation needed to prevent internal interference. In an NSDR setup, if the device starts transmitting on one link, the energy from that transmission can effectively blind its own receiver on the other link. It's like trying to listen to a whisper while you're shouting through a megaphone. To make these multiple links useful despite this limitation, the system uses clever timing techniques to manage interference. Instead of letting transmissions happen whenever they are ready, the device synchronizes the activity across both links. The goal is to align the end times of the data packets, known as PPDUs, so that they finish almost exactly at the same time. This is achieved by using padding, by adding extra dummy data to trigger frames or adjusting the length of aggregated data frames. The system can delay a transmission slightly so that it stays perfectly in sync with its counterpart. By ensuring the difference between the end times of these simultaneous transmissions is kept to a tiny margin, typically 8 microseconds or less, the device avoids a situation where a transmission on one link overlaps with a necessary reception on the other. This synchronization turns a hardware limitation into a manageable coordinated flow of data. In many modern wireless environments, devices are expected to manage multiple connections simultaneously to improve speed and reliability. However, building a device with a dedicated radio for every single connection is expensive and consumes a lot of power. This creates a challenge for smaller, battery-operated or cost-sensitive hardware that needs to stay connected to multiple links without the heavy hardware overhead of a full multi-radio system. This is where enhanced single radio operation provides a smart middle ground. Instead of having multiple active radios, a device uses a single radio chain but operates it in a highly intelligent way. The device stays in a state where it is actively listening across multiple links at the same time. It is effectively monitoring several channels simultaneously to see if any of them become active. The magic happens when the device detects incoming activity. If the device hears an initial control frame on one of those links, such as a duplicate frame sent by an access point, it realizes a data exchange is about to begin. The device then performs a rapid hardware switch, reorienting its single radio to focus entirely on that specific active link to complete the conversation. Because physically switching the radio from one frequency to another isn't instantaneous, there needs to be a small window of time for the hardware to catch up. To make this seamless, the access point manages the timing by adding specific padding to the end of that initial control frame. This padding extends the duration of the frame just long enough to cover the necessary delay required for the device to switch its radio. This ensures that by the time the hardware has finished reconfiguring itself, the rest of the transmission is ready and waiting, allowing for a smooth, uninterrupted connection despite the hardware limitations. In a typical wireless network, when a device gains access to the medium, it holds on to that airtime for a specific duration known as a transmission opportunity. Usually, this time belongs exclusively to the device that won the contention. However, we can significantly improve how efficiently we use the airwaves by allowing an access point to share its allocated time with other devices. This is known as triggered transmission opportunity sharing. Under this mechanism, when an access point wins a window of airtime, it acts as a conductor, deciding how to slice that time up and gifting portions of it to other stations. To start this process, the access point sends out a special trigger frame that signals to a participating station that it is allowed to transmit during the access point's window. There are two different ways this sharing can work. In the first mode, the sharing is quite restricted. The station being granted time is only allowed to send data directly to the access point. This is highly controlled and keeps the communication very focused. In the second mode, the station is given more freedom. It can choose to address the access point or it can communicate with other stations on the network, making the shared airtime much more versatile. For this to work without causing collisions or chaos, the participating station has to follow a very strict sequence. Immediately after receiving the trigger, the station must respond with a clear to send frame to coordinate the timing. From that moment on, the station must be incredibly precise. It has to ensure that its entire data transmission fits perfectly within the specific time slice the access point has carved out. By managing the medium this way, the network can squeeze much more data through the same amount of airtime. To achieve high performance spatial multiplexing, a wireless system needs a precise mathematical map of the environment, known as channel state information. We obtain this map through a process called sounding. Think of sounding as a way for the transmitter to probe the airways to see how signals bounce off walls and objects before it decides exactly how to shape its beams. There are two primary ways this sounding occurs. In the first method, known as non-trigger based sounding, the process is driven by the beamformer itself. It begins with an announcement, which acts as a heads up that a sounding sequence is coming. This is immediately followed by a null data packet or NDP. Because the NDP contains no actual data. Any signal received during this window is purely a reflection of the channel itself. The receiver then analyzes the signal and sends back its findings. The second method is more orchestrated and is used when we want to hear from many users at once. In this trigger-based approach, the system uses a specific trigger frame to solicit simultaneous feedback from multiple devices. This is essential for multi-user sounding, where the goal is to serve several clients in the same time slot. Depending on the goal, the feedback provided can take different forms. A device might report single-user beamforming information to help a direct connection, multi-user beamforming data to assist in complex spatial grouping, or a channel quality indicator which tells the transmitter the overall health and capacity of the link. Because these feedback reports are incredibly detailed, they can become massive, sometimes reaching over 60,000 octets. To prevent these large reports from overwhelming the connection, the system segments them into multiple pieces. These segments can be distributed across up to 6 separate frames within a single transmission block, ensuring the information arrives reliably and efficiently. When we move into a multi-link environment, we are essentially allowing a single device to communicate across several different radio links at the same time. While this massively increases speed and reliability, it creates a major coordination challenge. If every link tries to manage its own individual acknowledgement process, the overhead becomes overwhelming, wasting precious airtime just to keep track of what was actually received. To solve this, we use a more efficient approach to block acknowledgements. Instead of setting up a separate agreement for every individual link, we establish a single block acknowledgement agreed for each traffic identifier. This means that all data belonging to a specific type of traffic, like a high priority video stream, is governed by one unified agreement, regardless of which physical link that data actually travels over. This unified approach simplifies how the transmitter behaves. The transmitting side maintains one common transmit buffer and one single window control for that specific traffic type. It doesn't matter if the next packet goes out over link 1 or link 2. The device tracks its progress using the same set of rules and the same window of allowed packets. On the receiving end, we see a similar streamlining. Rather than managing dozens of separate queues, the receiver maintains a single reordering buffer for the entire device and the specific traffic identifier. This ensures that even if packets arrive out of order because they took different paths through different links, the receiver can reassemble them correctly in one place. To handle the different ways these links interact, the receiver can operate in different scoreboard modes. In one mode, it might keep the status of each link entirely independent, while in another, it uses a fully common scoreboard context shared across all links. This flexibility allows the system to balance complexity and efficiency, ensuring that multi-link communication stays fast without getting bogged down in management overhead. Wireless connectivity isn't a static setup. Devices don't just connect once and stay that way. They need to adapt to changing interference, mobility, and power requirements. This is where dynamic link reconfiguration comes in, allowing a device to add or remove active links while it is already operating on the network. When a device needs to change its connectivity profile, it initiates the process by sending a reconfiguration request to one of its existing active stations. This request can trigger two main types of actions: adding a new link or deleting an existing one. If the device wants to add a link, it provides a new link identifier along with its specific station profile, essentially telling the access point, I want to use this new channel. Here is how I operate. Conversely, if it needs to remove a link to save energy or clear congestion, it specifies exactly which link should be taken out of service. There are a few important guardrails during this process. If the system uses channel validation, The access point will verify the requested channel information to ensure the new link is viable and clear of interference. When it comes to removing links, the access point generally must comply with the request. The only exceptions are if deleting that link would leave the device with no way to connect at all, or if the request targets the primary link of a mobile access point that cannot operate in a non-simultaneous transmit and receive mode. Even after a new link is successfully added, it doesn't immediately start blasting data. To manage energy efficiently, newly added links initially enter a power save or doze mode. They remain in this quiet mode until the network performs the necessary mapping updates to formally enable them for active communication. This ensures that the device only consumes power on new links when they are truly ready for use. When an access point is being removed from a multi-link device set, the goal is to avoid an abrupt disconnection that could drop active sessions or cause network instability. Instead of simply cutting the signal, the system uses a coordinated process to signal an upcoming departure, allowing the clients to transition gracefully to other available links or access points. To initiate this process, the access point sends out BSS transmission management frames. These frames act as an early warning system, explicitly signaling to connected devices that disassociation or link removal is imminent. Within these messages, the system provides two critical pieces of timing information to prevent guesswork. First, it uses a disassociation timer, which essentially counts down the number of beacons that will be sent before the connection is officially severed. Second, it provides a specific timestamp that marks the exact moment the basic service set will cease to exist. For standard clients that aren't part of the multi-link group, this information is vital because it gives them the window they need to scan for new networks and perform a seamless handoff. The process is even more precise for multi-link devices. When a specific link is slated for removal, the system uses a reconfiguration element that includes a dedicated removal timer. This ensures that the link information is only deleted from the device's internal logic once the scheduled time has actually arrived. By synchronizing these timers across the network, the system ensures that the link deletion is a coordinated event rather than a sudden failure. This careful orchestration allows the network to shrink or reconfigure itself without the user ever noticing a disruption in service. When we use very wide frequency bands like 320 MHz, we want to utilize every bit of that available space to maximize speed. However, in a crowded wireless environment, it is common to find that a small piece of that wide channel is being used by another device or an interfering signal. In the past, even if a tiny slice of a wide channel was busy, the entire channel would become unusable, forcing the system to fall back to a much narrower, slower bandwidth. To solve this, we use a technique called preamble puncturing. Instead of abandoning the whole wide channel, the access point can essentially skip over or puncture the specific parts of the spectrum that are occupied. This allows the transmission to flow around the interference, utilizing the remaining clean parts of the whole wide channel without interruption. To make sure every device in the network knows which parts of the spectrum are off limits, the access point uses a signaling mechanism called a disabled channel bitmap. This bitmap acts as a map, clearly communicating which specific subchannels are unavailable so that all participating devices can coordinate their transmissions correctly. There are, however, important constraints on how this functioning can be used. We cannot puncture every part of the band arbitrarily. For example, the primary 20 MHz channel is the foundation of the connection and can never be punctured. It must always remain intact to maintain the link. In addition to that, certain types of critical communication are prohibited from using punctured channels. High priority transmissions, such as those requiring an immediate response or specific trigger frames used to coordinate multiple users, must use a contiguous, non-punctured channel. This ensures that the most vital signaling remains highly reliable and predictable even in a complex, interference-heavy environment. In a crowded wireless environment, devices often have to wait their turn to speak because they detect other transmissions nearby. This waiting period can significantly limit the overall capacity of the network. To solve this, we can use a concept called spatial reuse. Spatial reuse allows a device to transmit data even when it senses that another nearby network is already active, effectively allowing multiple conversations to happen in the same area at the same time. One of the most effective ways to manage this is through power spatial reuse. Instead of just transmitting at full strength and causing interference, a device carefully calculates its permitted transmit power. This calculation relies on a value known as the power spatial reuse input. To determine this input, the device looks at several factors, including the expected strength of the signal it is receiving, the specific error rate it needs to maintain for a reliable connection, and the interference thresholds by the surrounding overlapping networks. By balancing these factors, a device can find the sweet spot where it transmits with enough power to be heard by its intended receiver, but with low enough power to avoid disrupting the neighboring transmission. This calculated power level is then signaled through a specific parameter called a transmit vector. This parameter tells nearby devices exactly how much spatial reuse is being applied. However, spatial reuse isn't always beneficial. In some cases, a transmission might be too sensitive or too high priority to risk any interference. To protect these critical communications, the system includes a way to prohibit spatial reuse entirely. When a device receives a command to disallow spatial reuse, it must follow strict traditional rules, ensuring that the surrounding environment remains quiet and protected for that specific transmission. This balance between aggressive reuse for capacity and strict control for reliability is what makes modern high-density wireless networks possible. To maximize efficiency in high-efficiency wireless networks, we use multi-user operations to allow an access point to communicate with multiple devices at the same time. This happens in two different directions. The downlink, where the data flows from the access point to the clients, and the uplink, where clients send data back. In downlink multi-user MIMO, the access point manages how it divides the available spectrum. One critical constraint involves the bandwidth of the transmission. When an access point sends a signal, it cannot divide the bandwidth into smaller resource units or multiple resource unit groups to serve different stations if those units are narrower than the total transmission bandwidth, unless the receiving stations specifically support partial bandwidth operations. This ensures that the division of the spectrum is consistent with what the hardware is capable of receiving. When we move to the uplink, the coordination shifts. Instead of access point deciding when to send, it uses a trigger frame to tell multiple stations exactly when to respond. These trigger frames act as a conductor for an orchestra, ensuring everyone stays in sync. However, there are strict rules for these frames to maintain order. A trigger frame must be consistent. You cannot mix different formats such as combining high efficiency and extremely high efficiency frames within the same trigger frame sequence. In addition to that, the access point cannot trigger uplink MIMO within a specific resource unit unless the participating stations are explicitly capable of supporting it. Finally, we have to consider how the system handles group address frames, which are transmissions intended for multiple recipients at once. To ensure that every device in the group can successfully decode the message, the system enforces highly robust configurations. When sending these group frames, the transmission is restricted to a maximum of single spatial stream and must use a mandatory high reliability modulation scheme. This trade-off sacrifices raw speed to guarantee that even the most distant or obstructed device in the group receives the information clearly.